Welcome to this video. In the previous video, we have seen that if there are multiple senders trying to send their frames using a single channel, which is statically divided among the users, if the number of senders willing to communicate is lesser than the channel divisions, the channel utilization is very low, and if the number of senders is more than the channel divisions, then some of the senders will not be given access to the channel. So that is the problem of static channel allocation. The better way is to go for dynamic channel allocation. So the basic problem is how to give access to the contending senders, or how to give access to basically one of the contending senders, so that there are lesser channel or no channel frame collisions. So we'll see two such multiple access protocols, Aloha and carrier sense multiple access. In this particular video, we'll see only Aloha and its types. So the story started in 1970 on Hawaii Islands when Norman Abramson, a researcher, along with his colleagues, enabled a wireless communication between users in a remote island to the central computer in Honolulu. So basically, for them, laying down cables for that communication was not affordable. So they used uh, radio waves, short range radio waves between the islands and the remote computer in Honolulu. So here they use the same frequency for upstream communication, so that only one user at a time was able to send the frames, because if multiple users tried to send the frames, as the frequency was same, they will be garbled. So this basically was a candidate for the when there were multiple users or uncoordinated users trying to send frames. So this system, or the design which is given by Norman Abramson for such system, is called as Aloha. So there are two versions of Aloha. One is called as pure Aloha, where the time is continuous. That means any station or any user can begin sending its frame at any time. And slotted Aloha, the second version, where the stations or the users are given discrete time slots which are able to fit any frame, and the users are only permitted to send their frames in the beginning of their slots. We'll see each of them in detail. The first is pure Aloha. In this, each user is free to transmit whenever they have data to be sent. So obviously, if any user goes at any time, it may so happen that the two or more users are sending their frames at the same time. That may give rise to frame collisions. That means the frames are being at the same time in the channel. Multiple frames are there in the channel at the same time, and that's why there'll be collisions. They'll collide with each other, and ultimately they'll be all the frames, such colliding frames, will be garbled, collided. This is what is called as collisions that we have seen previously. Now senders needs, that's why the sending stations, they need to know whether there had been some collisions. Now in Aloha, when a station transmits its message to the central computer, the computer rebroadcasts the frame back to all the stations. Now this is how the original sending station can listen for the broadcast to see whether the same frame or the correct frame has been transmitted, so that if from the broadcast it is receiving the same frame, it could conclude that the frame has been successfully transmitted to the station, because then only the central transmitter can broadcast the same frame back to it. Now, if the communication was using wired systems, the sender, it was possible for the sender to listen whether there were collisions while the frame was being transmitted itself. In the case of wireless, only using the broadcast or the reverse communication, the sender can conclude whether there was some collisions or not. Now, if the frame is destroyed, the sender just waits a random amount of time and sends it again. Now, this is very important that the waiting time must be random. Otherwise, what will happen? The sending frames will collide over and over. Imagine one, two senders conclude that, or they um, got to know that their frames have been collided. So they each of them wait for a specific or a same time. Let us say, for example, 1 second, for example, and after 1 second, both of them once again send. Obviously, the frames will collide. Now, even after that, they wait for the same time and send once again. Now, this is going to happen. The collisions are going to happen over and over. That's why the waiting time for each of the center must be completely random. Now, we'll know the contention systems. What is meant by that? Now, these are the systems that use the same channel in the way that might lead to conflicts, or we can say collisions. So now once again, in this particular system where multiple senders are trying to send the same send their frames at the same time, there will be collisions. So these are the contention systems. Now this diagram depicts how in what different ways collisions can occur. So in the first, I mean, the channel is same. Just to make the transmission of different users visible, the different rows are visible here. Otherwise, the channel is same here. So this is the time going like this in X, and there are multiple senders like A, B, C, D, E, etc. Now, sender A transmits a frame. Let us say, for example, at the first beginning of the time, the station D transmits a frame. After some time, station A starts transmitting a frame. So before the frame has been received, or that has gone through the channel, before that has gone through the channel, station B starts transmitting its frame. So the A's frame and B's frame, they collide for a short span of time. So only fewer the last some bits of A's frame collide with some initial bits of B's frame. Similarly, before B's frame has gone through the channel, C also initiates its own frame, where just after B starts. That's why a majority of that part will collide with B's frame. Now, similarly, A's frame or second frame, if you can consider, also collides with D's frame in this given way. So just after D has started its transmission or the frame's transmission, just after a few time, A starts its own frame transmission, and the major part of that A's frame collides with D's frame. Now, whatever may be the amount of bits garbled, the checksum of the original frame will not match at the receiver, because some part or most of the parts has been changed. And that's why in any case of collision, that may be for a few bits or majority of the bits or the frame type, frame content, that is a collision. And that's why such collided frames have to be retransmitted. So this is what is shown here. Frames are transmitted completely at random time, and that's why there is some possibility of collisions. Some frames are not collided, whereas some frames are collided. If one frame is being transmitted and before it is going I mean, it has been completely transmitted. If some other station transmits its own frame, that is bound to collide with the first frame. So with that, let us now try to find out what is the efficiency of an Aloha channel. Now there may be, we'll take one example which is mimicking, or which will be exploring the Aloha system. Now let us say, for example, there is an infinite collection of users typing at their terminals. That means the stations. Now there are two states. Either the user is typing, and after typing, it will simply be waiting for the typed line to be transmitted successfully. Because after typing a line, when a line is finished, the user stops typing, waiting for the response. Now what is the response? The station, it will collect that line and then try to transmit that as a frame over the shared channel to the central computer, and the station will check once again whether the channel has transmitted that frame successfully. Now if the frame transmission was successful, the user sees the reply that the frame transmission was successful, and the user can now go back and start once again typing. Now if that frame was not successfully transferred, the user has to wait continuously while the station retransmits the frame over and over until it has been successfully sent. So these are the two possible scenarios. The frame, if the frame has been transmitted successfully, the sender can begin typing once again. Otherwise, it has to wait for the station and the channel to transmit the frame successfully. So at this point, let us define what is called as the frame time. This is the amount of time needed to transmit the standard fixed length frame. Very important thing here is that all the frames in the Aloha systems will be of the same fixed length. That increases the efficiency, that has been studied. So that is for sure. So frame time once again is the time needed to transmit the frame, or fixed length frame, which is the standard fixed length frame which is defined in the Aloha. Now each of the new frame is assumed to be generated by what is called as the Poisson distribution with a mean of n frames per frame time. Now what is this? Now from the queuing theory, we know that a Poisson distribution defines a queuing systems where the arrival times are completely random and they are independent of each other. That's why the inter-arrival times, that means the time between the two successive arrivals, is exponentially distributed. And this is the scenario in this Aloha systems as well. If you consider the events occurring as the number of frames being generated, so they are also independent of each other and they are being generated at completely random times. And that's why this system is modeled by Poisson distribution, where n is the mean number of frames per frame time. Now obviously, if that mean frame, the number of average number of frames generated per frame time is greater than 1, the user community is generating the frames at such a rate or a higher rate than the channel can handle, because frame time is the time required to transmit a frame successfully. If there are more than one frame, that is n, in the channel, collisions are bound to occur. Every frame will suffer a collision, and that's why for reasonable throughput, where there are less number of collisions, we can say, or no collisions, we expect that the mean frames per frame time, the number of frames per frame time, should be between 0 to 1. So this is the situation or condition, we can say. Now we have previously seen that when if some frames are there at the same time, more than one frame is there in this channel at the same time, in the same frame time, they are bound to collide, and the collided frames will be detected by the stations, and these collided frames will be retransmitted. So there will be original frames which are being transmitted, and in addition to that, if some of the frames are being collided, those frames will be retransmitted. So let us now assume that the new and the old frames combined together are modeled by a Poisson distribution with mean of g frames per frame time, where g basically is greater than or equal to n. N is what? It is the mean number of frames generated for per frame time. So G will now include the additional retransmissions, and that's why it will be greater than or equal to n. If there are no collisions, G is will be equal to n. If there are some retransmissions, collisions, there will be some retransmissions, and that's why including those, G will be greater than n. Now, when there obviously the same thing, when there is a low load, that means the number of frames itself, the mean number of frames generated per frame time itself is very low. N is nearly equal to 0, and that's why if the number of frame itself is very low, there will be few collisions, and that's why few retransmissions. And that is the reason if there are a few retransmissions, G is likely to match N. If the load is high, on the other hand, there will be many collisions, obviously, and that's why combining those with the original frames, G is greater than N. Now, if you consider P0 as the probability of a successful frame transmission, and the average number of frames, or let's say for example offer load is G, means there are G number of frames being offered to the system or to the channel, where P0 is the probability of a frame being successfully transmitted. The throughput of that system, which is S, can be calculated to be the total number of frames offered multiplied by the probability of the successful transmission. That is, S is equal to G into P0. Now, we have already seen, we will now see what is called as when there may be actually collisions. So that is in relation with the frame time. Now imagine what is shown here to be a shaded frame, that is the frame we want to transmit. Now the frame time is t here. So the time starts at t0, at time some t0 plus t. So after one frame time, the actual shaded frame is being generated and it is being transmitted. So if any frame is generated between the time instance t0 and t0 plus t, if anywhere between these time instance, if a frame was already there, what will happen? If it is already there, some part of it is bound to collide with this frame. If it is there somewhere between t0 and t0 plus t, that collides with the start of the shaded frame. This part, that is the end of the previous frame, will collide with the start of the shaded frame. Similarly, if after this shaded frame was generated and being transmitted, which was rather in the channel from time t0 plus t up till t0 plus 2t, because the frame time was t, and if any other frame was generated in that time duration between t0 plus t and t0 plus 2t, the start of that new frame is going to collide with the end of the shaded frame, because we should always see that the time is going like this. So this was the first frame, and before it was successfully transmitted, our shaded frame was generated, and it collided with the end of that original frame was collided with the start of the shaded frame, whereas the third frame that we have considered here, which was generated between the time t0 plus t and t0 plus 2t, is generated before the shaded frame has been successfully transmitted through the channel, and that collides with the end of the shaded frame. The crux of, or the conclusion here, is that if any frame, while the shaded frame with the frame time of t is being transmitted through the channel, if any frame is generated anywhere between t0 up till t0 plus 2t, either from this to this, that is t0 plus t, or t0 plus t up till to t0 plus 2t, which is exactly equal to 2t, double the frame time, that particular frame is surely going to collide with the shaded frame. And that's why this 2t time is called as the vulnerable time for this shaded frame. There should be no frame generated in this vulnerable time for the successful transmission of the shaded frame. This is the vulnerable time, vulnerable period, we can say. The probability that k frames are generated during a given frame time in which actually g frames are expected. Now this can be modeled by the Poisson distribution, as we know. Now the probability of k frames where actually g frames are expected is given by g raised to k into e raised to minus g upon k factorial. We know that in that particular frame time, no other frame should be generated. So the probability of 0 frames generated is, we can calculate that by putting k is equal to 0. So g raised to 0 will be 1 and 0 factorial will be 1. So probability that 0 frames will be generated is simply e raised to minus g. So we have seen that the interval was 2 frames times long. 2 frame times long. So the mean number of frames generated in 1 frame time is g. So the mean number of frames generated in 2 frame times is 2g. Now probability of no frames being initiated during the entire 2t or the entire vulnerable time is obviously t0, using the same calculation or the same equation, putting k is equal to 0 for the vulnerable period, that is 2t, where the mean is now 2g. We get the probability of no frames generated, p0 is equal to, in the instead of e raised to minus g, we get it to be e raised to minus 2g. So using the previous equation, the throughput was calculated to be g into p0. If you simply put the value of p0 into this equation, we get s is equal to g into e raised to minus 2g. So using this equation, we can now plot the relation between the offered traffic, that is g, and the throughput s, that is given in the next slide. So here is the plot of g, that is the number of frames attempted per packet time, or per frame time we should say, and the s, the throughput per frame time. So this is plotted here for pure Aloha, where we see that using that equation, previous equation, we know that where g is equal to 0.5, s is 0.18, that is 18%. The throughput is 18%. That is the maximum throughput that we are getting when g was 0.5. So now we'll see the next version of Aloha, that is called as slotted Aloha. Now a scientist called as Roberts in 1972, with his research, doubled the capacity of an Aloha system. Previously we have seen that pure Aloha system, the throughput was only 18%, and here for slotted Aloha it comes out to be double of that, almost about 36%. Now this was achieved by dividing the time into discrete intervals called slots, where each of the interval corresponds to one frame. And this is how it halts the vulnerable time, or the vulnerable period, we should say, because only we should take the care that now instead of the continuous time, there should be no frames generated in that one slot only. So this is how the danger, or the danger period, is now reduced half. So users only have to agree on slot boundaries, because they need to know which is the slot, or where the slot is beginning and where it is ending. And that's why synchronization is required. So there will be one special station that emits a pip at the start of each interval, like a clock. So in slotted Aloha, basically there are some restrictions. Previously we have seen in the case of pure Aloha, anywhere when the station has got a frame to send, it can send, giving rise to some collisions at some time. So in the case of slotted Aloha, a station is not permitted to send whenever the user types a line. Rather, user waits for the beginning of the next time slot. And this is how the continuous time Aloha is turned into a discrete time one. Now let us calculate the probability of no other frame during the same slot as our test frame. That is, using the same relation, we can calculate that e raised to minus g. So which once again gives the throughput g into e raised to minus g. So with that, if you plot once again the slotted Aloha, the throughput against g, the attempts per frame time, so we get the peak throughput at g is equal to 1. Previously for pure Aloha, we were getting the peak, or the maximum throughput at g is equal to 0.5. Here in the case of pure slotted Aloha, we are getting the maximum throughput at g is equal to 1, and that is 0.367 or 37%, which is double the throughput of the pure Aloha. So in the best case scenario, 37% of slots are having no frames, that's why they are empty, and 37% of the slots, I mean 37% of the time, that will be, there will be success. That means the slots will be having exactly one frame, and rest 26% there will be more than one frame in the slots, and that's why there will be collisions. So this is how we have seen the one such protocol for managing the shared access for multiple users, which is called as Aloha, and its types, the pure Aloha and the slotted Aloha. Thank you.